Okay, let's work through the questions that we would have done in lecture. Our first question, write the Lewis symbols for the following. We always start from the basic atom to figure out where we're going. So hydrogen is that first question. Hydrogen minus is the ion, but hydrogen itself would have had only one electron. Hydrogen minus means there are two electrons, so we'll put a double dot there. They would have appeared in the 1s orbitals in the ground state. Tin, Sn 2+, tin itself is in the fourth column of the periodic table underneath carbon. So tin has 4 valence electrons, and the +2 charge means it only has 2 valence electrons left. Potassium is similar in that we start again with the normal valence state of the atom. So potassium has 1 valence electron, and the plus means it's gone. So no valence electron. The bromide, bromium itself, has 7 valence electrons, and the negative charge means there's 1 more for a total of 8. So bromium has a completed octet. It looks like a noble gas. Selenium is 2 minus here, and selenium is in column 6 underneath the oxygen. So selenium has 6 valence electrons, and the -2 charge gives it 2 more for a total of 8. It looks like an octet. Scandium, Sc, if you look in the periodic table, Sc is a 3d1 element. It exists in that 4th row of the periodic table, the first entry into the D block, so it has a total of 3 valence electrons. So +3 means they're all gone, and so scandium can be written like potassium with nothing in its valence shell. It's empty. If we move now on to the next question, assign formal charges to each of the atoms in the following structure. When we're drawing Lewis structures, we really should have that table of valence and hypervalence at our fingertips. So I'm going to draw it out right here. So we have 1, 2, 3, 4, 5, 6, 7, 8. That's the columns of the periodic table. And the valences are 1, 2, 3, 4, 3, 2, 1, 0. So the valence of a column 8 element is a noble gas. There's 0, and it has 4 electron pairs. Fluorine has 3 electron pairs, oxygen 2, ammonia, the nitrogen in ammonia only 1. So those are the valences of any n equals 2 atom. If I have a hypervalence possibility, if I've got atoms of n equals 3 or greater, then I can split up the lone pair and make more bonds. So I can make a total of 5 bonds if I split up my lone pair there. I can make 4 bonds or 6 bonds here, split up the lone pairs once and then a second time. Same thing here, so 1, 3, 5, 7, 3, 2, 1, 0 is my valence states. 0, 2, 4, 6, 8, 4, 3, 2, 1, and finally 0. Notice that the most number of bonds that a neutral atom can have is always the column number that it's in. So that is, of course, if it's got the d orbital. So it can't do that if it's, for example, column 5. Can't do that if it's nitrogen, but right below that phosphorus has some d orbitals, so I can make 5 bonds on phosphorus. Now, when I look at these structures, let's first look at the carbon in here, and I see a carbon with 4 bonds on it. So it looks exactly like that. So that carbon is neutral. Here, however, this second carbon over here, I see 3 bonds and 2 electrons in a lone pair. So in that carbon that I've highlighted in yellow looks like this. It looks like 3 bonds and 1 lone pair. So I've given it 5 electrons, which means that carbon is where the -1 charge is. So if I was going to redraw that showing the negative charge, I would have hydrogen, carbon, 1, 2, 3, carbon, lone pair, and a negative charge on that carbon. So that's where the formal charge is for that carbon. Now let's look at the next one. If I look at the carbonate ion here, so I see that there's 2- charges on this species. I look at the oxygen, at the various elements, and the carbon in here, I'll just highlight them as I go through. So the carbon that I see here has 4 bonds on it, so it looks like carbon. This oxygen with the double bond has 2 bonds and 2 lone pairs, so it looks exactly like right there, 2 bonds and 2 lone pairs. It's good. The other 2 oxygens, they each have only 1 bond on them and 3 lone pairs. So those 2 oxygens look like that. They look like a fluorine. They have a -1 charge on them. So if I was to redraw that one showing the charges, then I'd have carbon double bond to oxygen with 2 lone pairs. I'd have single bond to oxygen with 3 lone pairs and a negative charge. And I'd have another single bond to oxygen with 3 lone pairs and a negative charge. So you always circle the charge so you don't mistakenly think it's just another lone pair or something like that. And finally, we have this interesting looking species, CH3, CH3 with an overall plus charge on it. We better draw that out better. That's just not very good Lewis structure. We can't see where everything is. So I'm going to draw it out a little more explicitly. I'll start with the CH3 here. So carbon with 3 hydrogens. And then a carbon with 1 hydrogen. And then a carbon with 3 hydrogens. Now when I look at that and I compare it to that table of valence and hypervalences, I see that the 2 carbons on the end, so right there and right there, are neutral. They have 4 bonds, so they look exactly like a carbon should. This carbon in the middle, though, I see only 3 bonds. And if I look at my table of valence and hypervalence, the 3 bond element is right there. So I've made my carbon look like a boron, carbon column 3. And that means, since boron only has 3 electrons, this carbon has a plus charge on it. So that's what's called a carbocation.